So this problem is what I consider to be the hardest problem in the course. It's a homework problem. It will not show up on an exam, but I do want you to understand it and enjoy it. And what we're asking is we have this setup. We have a lighthouse that's on an island. It's 3 kilometers from the shore. And we have the question, if it's going 4 revolutions per minute, 3 kilometers away, the question is, how fast is the beam moving relative to what, right? On the shore, when it's 1 kilometer from P. And I've drawn up above what your first instinct might be for a diagram. It's also not a useful diagram. I want you to first of all visualize what's going on is that this lighthouse is going around 4 times, so there's like some kind of light coming out here, some kind of hopefully a Fresnel lens or something, and it's shooting out light, and it's a pretty narrow beam, but it's not totally narrow. But you could imagine that you just have a single laser light, if you wish, that is running around, so the math is the same. And so the point is, I want you to imagine you're standing right here on the shore, and you're going to see that laser light swing past your feet pretty quickly. If there's a whole shore, then that little laser light, how fast is it going past your feet? But if there's a little guy over here who is 1 kilometer away, how fast is the laser light going past that person's feet? And you've probably seen this kind of thing before. So I want you to imagine these searchlights. More likely you've seen it from an airport rather. So a small airport, maybe you're driving by at night in a small part of the world, not inside a big city, and there's an airport nearby, and you see searchlights kind of in the vicinity. Sometimes you've seen these at carnivals, things like that. If there's a small carnival in a small town, and then they have these kind of like searchlights to draw your attention to it, those kind of things. So hopefully you've seen something like this before, and you understand that it's going to be a different speed in those 2 spots. I've drawn a little diagram to help you visualize again what's going on. Suppose that this is the width of your searchlight right here. And so you're going to cover this much width in a certain time. But if you look from here, from this perspective, all these angles are roughly the same. I try to draw them the same. Okay, so if you were to draw a circle around here, I would hope that you would agree that this angle is the same as this angle is the same as this angle. At least it's good enough for what we're talking about. So this beam that's coming out, this beam that I'm coloring in, that's equivalent to this beam, which is equivalent to this beam. So as the light goes away from point P, so here's your lighthouse right here. Here's your lighthouse shooting out a beam. This is how, let's say, wide the beam is to the guy standing 1 kilometer away, for example, and then maybe this is somebody 1/2 kilometer away. These are just ideas here. You notice that the beam width is going to be much larger, but also the important thing is the beam has to travel further in the same amount of time. So even though over here, from the perspective of the lighthouse operator, the beam is going at a constant angular velocity, right? It's just rotating around at a normal constant speed. But when you project that onto the shore, it's going to appear that when you're at point P, it's going to be moving the slowest, and then it's going to speed up. So for the person who's far, far away, it's going to feel like it just flicks by, really, it's going to be faster, right? Does that make sense? Hopefully it does. If it doesn't, then pause the video here and think about it. Rewind this piece of the video and hear this discussion again until this part makes sense. Okay, so I've drawn a triangle in blue to echo what's happening on the left-hand side of the screen, and I've labeled it. So your lighthouse is 3 kilometers away, so all these units are in kilometers. This is kilometers, so we're 3 kilometers to the left of point P, which is your origin, and we want to know how fast the beam is moving when the beam is 1 kilometer away from P. So what it means is y is currently equal to 1, but the point is y is varying. So we're saying y equals 1, but what we really mean is let y vary, let theta vary. So when this guy is changing, this guy is changing. Theta is changing and y is changing. X is fixed because we can't move the lighthouse. But y is changing, and then we're going to take the derivative with respect to, you know, time or something using, I don't know, related rates, right? And then what we're going to do is we're going to plug in y equals 1. Okay? So y is varying for this problem, but then we'll plug y equal 1 in. If you plug it in too soon, then you can't take the derivative with respect to y. Okay? So what we have is a trig problem. I'm going to just cut this out and move this guy over. Right? Now I want to analyze what's going on, and what we have is tangent of theta. So remember what we did in class. We said if you have on a right triangle, if you have one leg and want the other, you use tangent. So like if you have a leg, want a leg, use tangent or cotangent. If you have the, you have the hypotenuse and you want a leg, you typically use secant or cosecant or cos, I forget which one. I told you all the ones that you would do. I told you like what to do in class. So definitely we have the situation where we have a leg and want a leg, so we're definitely going to use tangent. Okay, so we know we're going to use tangent. Tangent of theta is what? Is y over x, and y is unknown and x is 3. So this is our setup. And this is also equivalent to saying sine of theta over cosine of theta. So all these are information that we might use in the problem. So we have 6 trig relations, but this is the one that's useful for this problem. Cotangent would also work, but we don't have, cotangent is not something that's typically used. You typically go for tangent. Okay? So the problem is generically, okay, tangent of theta is y over 3, and we want to find out how fast the beam is traveling on the shore. So we're going to see how fast y, so what we want is dy dt, but what do we have? We can find the following. We can find dy d theta, or you can flip it, d theta dy. Those are things we can find. And we also have, from the word problem, we know what this is in radians per minute. So this is information we need to make use of. But we can find out d theta dt and dt d theta. So here's all the pieces. This is kind of like your word bank. These are the things we can find or calculate, and this is what we want. So let's put together a picture of how we're going to solve this problem. So dy dt is going to be made up of something, which is dy over something, and then the same something has to go in both of these positions, and a dt goes over here. So what do we have of the things that we already know or can calculate? What pieces will help us get there? Okay, we have a dy over d theta. Okay, that's fine. When we need a d theta over dt, and we have one of them. So this is what we're going to do. We're going to go ahead and use this version of the related rates. So there's two things. There's related. Hold on a second. Okay, I just wanted to make sure I wasn't lying to you. Yes, so this is from the related rates section, but the reason I pause is because I'm just using the chain rule. And this is an important thing, 3.9. We say related rates. It's kind of a code word for just use the chain rule, which we've had longer than now. Okay, so we have two words that are basic, that related rates and chain rule are both coming into play. We call the problem a related rates problem, but we call this green thing here the chain rule. So the chain rule is at the heart of your related rates problem. So let's go ahead and try to figure this stuff out. I'm going to cut this because I don't need it anymore. I'm going to move this guy up. And I don't need this anymore because I already know what it is that I'm looking for, right? So I got to put all those pieces together. So what do you want? Dy dt is dy d theta. So what I'm going to do is I'm going to just sketch out for you the remainder of the steps. Your steps go like this, because it's your homework problem, right? Find dy d theta using implicit. I'll pause this while I'm making your list. Okay, so you want to find dy d theta using implicit differentiation, so I'll let you do that yourself. And you do that on the function tan theta is y over 3. And my hint is the derivative of tangent is secant squared. And then the second thing you need to do is find d theta dt from the problem statement. We actually already calculated that over here. So pretend like I didn't tell you that. You figured that out yourself. Then you just put all the pieces back in, and it should work out for you. Okay, good luck.